So is there a way to measure similarity between two vectors? Let's say if I have vector 1, let's call this A, or let's just call this A, vector A. And let's call vector B, let's say this vector. They're pretty similar to each other, right? A and B are pretty similar to each other. But if I have another vector, vector C, they're facing in opposite directions, right? They should have some sort of negative similarity. And so how can I express similarity in terms of specific vector operations? And so a dot product is how you would do that. Now, the reason why doesn't seem clear at first. We'll slowly build up to the idea of projections, but right now, let's just define what the dot product is. So it's very, very simple. If I have a vector A, and let's say that's equal to, I don't know, 0, 1, B, let's say X component is, I don't know, 3, Y component is 4, just making these numbers up. But dot product, you basically take these components and you multiply them out, and you just add up their results. So 0 times 3 is 0, 1 times 4 is 4. So that's going to be the dot product. It always returns a scalar value. So you input in these two vectors, and your output is a scalar. Now, dot products can be extended all the way up. So imagine if A was a vector, right? Imagine if A was a vector where the first term is, let's say, A sub 1, A sub 2, I'm just making this up, right? A sub 3 all the way up to A sub n. And then let's say B has the components B sub 1 in the x dimension, whatever dimension we're going to, right? Because vectors, believe it or not, vectors can be in a very high order dimension. Like there's the third dimension, second dimension, and then like you could go all the way up to infinite many dimensions, right? There can be many, many numbers representing the direction of vectors. And that's actually, a lot of that is actually used in AI, believe it or not, something called embeddings. But let's get back to the task here. The dot product is basically defined as the sum from I is equal to 1 to essentially the first terms, all the way up to the nth. You can think about it as the nth dimension, and you basically just multiply out these two terms and just sum it all up together. That's the dot product. Now, most of this video, and maybe in the future videos, we're only going to be dealing with dot products for, 3 dimensions or maybe 2 dimensions, probably restricting ourselves to 2 dimensions in this video. Therefore, the formula is just going to be A1 times B1 plus A2 times B2. Very, very simple. That's going to be the definition of the dot product. I'm just going to call that dP, okay? And so, dot products, let's try to visualize this, and let's see if we can come up with a proof for a pretty nice formula, okay? Let's say if I have 2 vectors. Let's call this vector A. And then let's say that I have another vector down here, vector B. Notice how these 2 vectors create an angle, which I'll call theta. Okay. What else can I do? Now, I've drawn a third vector here. What do you think this is? What can we represent this with? Well, imagine if, like, I'm just making this up. Let's just say this is the origin, right? The displacement is basically represented by vector A. The displacement is represented by vector B, right? If we were to think about vectors as essentially displacements. And so this would be the displacement going from, if we went from B to A, right? So we can write this as A minus B. This is the vector of A minus B, okay? Now, you got to recall a formula. This is going to be the cosine formula, and specifically, the formula is c squared is equal to a squared plus b squared plus 2ab times cosine of theta. All right, remember this is the law of cosines. And real quick, should be a minus, sorry about that. So yeah, this is the law of cosines, and essentially this c squared right over here represents the angle, the side that's across from the angle. So theta represents the angle that you're looking at. C squared represents the side opposite to that angle. And then a squared, b squared, those are just your other sides. So in this case, c squared would be represented by a minus b squared, and theta would just be this theta, and then a and b would just be a and b, okay? So let's just plug everything into the formula and see what happens. Now, remember that, well, when we're trying to use the law of cosines, well, these sides right over here have to be scalar quantities. But luckily, we know how to convert vector quantities to scalar quantities by finding just like the magnitude of the vector, right? We could just represent the vector by the magnitude, and then all of a sudden you would just get like a nice triangle, right over here. So you get that c squared, which is just the magnitude of a minus b squared, is equal to a squared plus b squared minus 2 times magnitude of a, magnitude of b, times cosine of the angle. Now, let's say that the vector a, and I'm sorry if I'm really inconsistent with the capitalization. I'm just going to make this lowercase a, lowercase b. This is pretty sloppy by me, so sorry about that. But all right, let's say that vector a is represented by, let's say, a1, a2, right, as its components. And let's say that vector b is represented as b1 and b2. So now we're going to try and simplify all of this using the components. All right. So a minus b squared, the magnitude of a minus b squared. Well, what's a minus b? That's just a1 minus b1 and a2 minus b2, essentially squared, right? So I'm just going to write that out. So I've just broken everything down into its components. And note that if I'm trying to take the magnitude of vector a, right, we saw that from the last video, that's just going to be the square root of the x component squared plus the y component squared. So if I'm trying to find the magnitude squared, well, then that's just going to be the sum of the squared components, right? Because then the square root gets erased out. And so it's just going to be x squared plus y squared. Or in this case, a1 squared plus a2 squared, which is exactly what we have here. And same goes for magnitude of b squared, right? b1 plus b2 squared. And then on this side right over here, well, we have the component a1 minus b1 squared and then a2 minus b2 squared. So there we go. Now let's see if we can shift the cosine to this side. Let's move everything here to the other side and see what happens. Now, as a challenge exercise, now that I've kind of isolated this part right over here, I want you to try and complete the proof. All right. Now, it's going to be quite a bit of algebra because you're going to have to FOIL everything out. But it turns out that the squares nicely cancel out, and you actually get that a1 times b1 plus a2 times b2 is equal to the magnitude of a, so equal to the magnitude of a times the magnitude of b, and then times cosine of the angle. Okay? And so what this means is that, well, what is this? This is the dot product that we mentioned earlier, right? And so therefore, we can say that the dot product between two vectors, which is symbolized as a dot b. So when you have the dot product, the notation is a, and you put a dot here, hence why it's dot product, b, and that's going to be equal to the magnitude of a times the magnitude of b times cosine of the angle. And once again, I'm sorry if my symbols are inconsistent right here or right here. Yeah, I should have fixed that, but it's all good. Now, why is the dot product important? Well, let's bring up a coordinate plane to help soothe our quest for knowledge. And we can see that, well, let's say if I have a vector, just a regular old unit vector, 1, 0. And let's say that I have a vector that's perpendicular to this. Let's say if this vector over here is 0, 1. If I take the dot product between two perpendicular vectors, notice how 0 times 1 gives me 0, and 1 times 0 gives me 0. So when I add these two values together, I just get 0. And so when a and b are perpendicular to each other, that's going to give you a dot product of 0. And it turns out that it works for no matter which two vectors it is, as long as, it's perpendicular to each other, the dot product of those vectors are going to be equal to 0. So I can say that if a is perpendicular to b, then that's going to mean that a dot b is going to be equal to 0. And likewise, if a dot b is equal to 0, then a is perpendicular to b. If a and b are very similar to each other, let's say if a and b are pointing towards the general kind of, area. Let's say if b has the coordinate, 1, 1. So generally, they're pointing towards the same direction. If I take the dot product, then what you'll find out is that, well, 1 times 1 is 1, 1 times 0 is 0, 1 plus 0 is 1. So whenever two vectors are facing very closely to one another, you're going to have a dot product that's positive, right? And so a would be greater than, or a dot b is greater than 0 if it's kind of similar, right? If they're pointing towards the general direction. And once again, keep in mind that these rules also apply for higher dimension vectors as well. So also keep that in mind. And finally, if you have vectors that are pointing in, let's say, complete opposite directions of each other, let's say if I have a vector that's pointing this way, that has the coordinates -1, 0, well then if I take the dot product between these two vectors, well, -1 times 1 is -1, and 0 times 0 is 0. I add those two things up, I get -1, I get a value that is negative. So when the dot product is less than 0, that tells me that it's not really similar. These two vectors are not pointing in the same general direction. And so this formula and kind of these three facts, you should probably memorize them, all right? But we've seen how, well, you can use like very simple examples and you'll see that these things are true. Now, dot products are very, very nice because they're actually connected with lengths. What do I mean by that? What does it mean if, let's say, if I have a vector A, and let's say if it has the components A1, A2, A3. Okay. What does it mean if I take the dot product of this vector A with itself? Well, if I take the dot product of A with itself, that's just going to be the magnitude of A squared, right? Because notice how when you take the dot product, right, what you're essentially doing is you multiply, in this case, A, each component of A by itself, so it's squared, and you add it. So it's going to be A1 squared plus A2, and you square it, and then plus A3, and then you square it, right? And from the Pythagorean theorem in 3 dimensions, we know that we can get the magnitude of A by doing the square root of A1 squared plus A2 squared plus A3 squared. And so if we square both sides, we get that the magnitude of this is equal to, well, what we have here, A1 squared plus A2 squared plus A3 squared, right? So we can think about this algebraically. There's also a geometric interpretation for this. So imagine if you're on the coordinate plane and you're dealing with the same vector. So you have, this is vector A, and then you have another vector on top of vector A that's the exact same vector. Because these two things are the same vector, the angle between them is going to be equal to 0. Therefore, these vectors are going to be kind of, you can think about it as perfectly similar, I guess. They're perfectly in the same direction. And the angle that's between these two vectors is going to be equal to 0. So if I plug this into my other equation, right, the magnitude of A times magnitude of B times cosine of theta, well, instead of A dot B now, this is going to be A dot A. And instead of the magnitude of B, it's going to be the magnitude of A. And cosine of 0, right, because we figured out that it's the same vector, the angle between them is 0, cosine of 0 is equal to 1. And therefore, this is just going to be the magnitude of A squared. So you can think about the dot product geometrically as well and algebraically, which is both really, really nice. I know this seems like a lot, but just know that like we're going to do some practice problems and you're going to have this solidified, and just know that there's going to be a lot more to dot products. Like it seems like such a simple operation, but then at the end of the day, it's like a completely different field. Like linear algebra, a lot of it is dot products. So yeah, that is pretty scary to think about. Another thing to note is that now that we've learned dot products, right? Think about it. Imagine the kinds of problems that we're able to solve. Like let's say if we're given 3 different points. This is, let's just say this is point Q or PQR, right? And so if I want to find the angle, you know, between these points, if I want to find the angle between, you know, QP and QR, well then, now I can use the dot product formula, right? Now I can try and find this cosine of theta part because now I know the definition of the dot product, right? I can do the dot product on this side, I can find out the magnitude of A and B, and then I can divide both sides by the magnitude of A and B to find cosine of the angle. I take the inverse cosine, and so I'm just setting up like a mind map for y'all so that you guys know, like, you know, how to apply what you've learned to, you know, these different problems in creative ways. So now we're actually going to go into a little bit of linear algebra. And so vectors, you usually see vectors as like, you can write them as just like a little review. You can write them using these brackets. You can, or sorry, these greater than less than signs or HTML signs, whatever you want to call them. You can write this out using I hat, J hat notation. So this would be 3i plus 3j. And if there was a z dimension, then you would add k to that. Or in linear algebra, a very common way to express a vector is using these brackets. So the x component would be on top, the y component would be on bottom, and if you had a z component, it would be below that. So everything is kind of like in order. And so vectors in linear algebra, it's kind of like x when you're referring to algebra. So recall back to just regular old algebra, right? The whole point of algebra, you know, is dealing with the unknowns. Like you have x is equal to 3 plus x squared or something, and you got like solve for x. And so this is like the root, or I guess like the atom, I guess, of algebra. Well, kind of the fundamental component of linear algebra, would be the vector. And specifically, there's something called a matrix. So in linear algebra, the vector is kind of like the unit of, or the source of life for linear algebra. And you have something called a matrix, okay? Now, some people view a matrix as just something that's able to store information. So for example, let's say if I create like a little table here. Let's say if I was setting up a survey about, so let's say this is or male, this is female, this is likes YouTube, and then this is going to be likes TikTok. Let's say that I set up like a little survey at my school to find out how many males and females like YouTube and TikTok respectively. And so let's say three males like YouTube, 10 males like TikTok, 5 females like YouTube, and 7 females like TikTok. So you can see how this is kind of represented in like a matrix, right? This can be used for storing information. But if you were to ask people in linear algebra or even in like artificial intelligence fields, like linear algebra is very popular there because it all comes down to matrices. So there's something called matrix multiplication. And what matrix multiplication does is it's like a set of operations basically. So like just how like we multiply two things, that's like an operation. Matrix multiplication is just like another operation. And so let's say if I have the unit vector in the I direction, and let's say if I were multiplying it by a matrix. Now let's make the matrix simple. Let's say if I have a matrix like this. I know I'm saying that word a lot, so yeah. But what you essentially do for matrix multiplication is you multiply, for 2 by 2 at least, you multiply the top one by the top one of the second one, so 2 times 1 is 2. Then you're going to add that to the second one by the second one. So 0 times 0 is 0, comma, and then now you move down to the row down here, and 0 times 1 is 0, and 2 times 0 is 0. So that's just a rule for matrix multiplication. I'm just going to give you another example because I know I went pretty fast with that. So let's say if I have 3, 7, actually let's do a 3. Let's do a 3 by 3 matrix. Let's say if I multiply this big matrix by this vector, 4, 2, 3. So what you essentially do is you're going to go for this matrix to the left, you're going to go row by row. So this row first, then this row, then this row. And basically what you do is it's just a dot product between the first row or the row you're looking at and the column of this matrix. So the dot product between 3, 5, 7 and 4, 2, 3, well, 3 times 4 is 12 plus 2 times 5 is 10, and then 7 times 3 is 21. So that's going to be the first component. And every row that you go down, well, that's going to be another component of the vector that you get as a result, okay? So in order for matrix multiplication to apply, all you need is just the number of rows you have to be the same as the number of. Now, what you actually see for matrix multiplication is that in order for me to actually do this operation, the number of columns that I have in my first matrix, which I'll call A, so the number of columns, notice how I have 3 columns, that has to be the same as the number of rows in my second matrix, right? So if I have a matrix A and I have another vector, or this can also be another matrix, it doesn't matter. The important thing to know is that the number of columns of matrix A has to be equal to the number of rows of matrix B, or vector B in this case. All right. And so let me just continue this problem. So now I take the dot product between the second row and the first column. So that's going to be 20 plus, and then that's going to be plus 8. And then 3 times 3 is 9. And then the final component is going to be 7 times 4, which is 28, plus 2 times 2 is 4, and then 5 times 3 is 15. And so I can add all this up. So that's going to be like 43. And that's going to be like 37. And that's 43 plus 4, that's 47. Okay, so that's the resulting vector that I get from this big matrix multiplication. Now, let me give you another example, just so that you guys have mastered matrix multiplication, okay? It's just a bunch of dot products. So let's say if I have a 2 by 2 matrix, And let's say if I try and multiply it by this matrix right over here. So in this case, there's 2 rows and there's 2 columns. And then for this matrix, there's 2 rows and 2 columns. And in order to remember the rule, what I'd like to a little trick to help me memorize this is that the columns of matrix A has to be the same as the rows of matrix B. So you can see the columns have to be equal to the rows, okay? And so you can view it as the inner shape of these matrices, right? The column of A, row of B, they're like the ones that are actually touching in this image, right? These have to be equal to each other. So if I have a 2 by 3 and I multiply it by 3 by 2, notice how the inside here is the same, meaning that, yes, we can do this. But if you were to get a question like, is this compatible? Right? If I have a 2 by 3 matrix and a 5 by 2 matrix, is this compatible? No, this would not be. And you can view this on the inside here. They're not equal to each other. So that's just a little trick that I use to help me memorize that. Anyways, let's go back. So let's actually write this out. So because if I multiply a 2 by 2 matrix by a 2 by 2 matrix, the resulting matrix shape is also going to be 2 by 2. So one way you can memorize this, once again, another trick I use to memorize the shape of the matrix that you get when you multiply 2 together is that you just delete the insides. So you just get 2 by 2. If I have a 5 by 3 multiplied by 5 by 4, well, then the resulting matrix shape would just be 5 by 4. Okay? If I have a 6 by 8 and an 8 by 2, the resulting shape is just going to be 6 by 2. Okay? And so what am I going to do? So it's just going to be dot product of first row and first column. So that's going to be 10. And then 6 times 4 is going to be 24. And then now we're going to go for the dot product of first row and the second column. So you want to go through these columns taking priority. So notice how first row, second column, that becomes first row, second column of our result in this matrix. So 2 times 3, that's going to be 6. And then 6 times 2, that's going to be 12. And now I'm going to move down, dot product between second row and first column. So 2 times 5 is 20. 8 times 4 is 32. And then finally, the dot product between second row and second column. So 4 times 3 is 12. And then 8 times 2 is 16. Okay, so that's how you would do this. So if you want to just visualize what we did, right? First, second, second. Okay. I don't want to bore you with my boring explanations in math, so I want to show you something cool. So notice how I have a 3 by 3 matrix and I'm multiplying by a 3 by 2 matrix. So the resulting shape I get is a 3 by 2 resultant matrix. Let's see what happens. Wow. And then, so this is just like the dot product visualized all together, right? And now, there we go. Notice how we get a 3 by 2 matrix as a result. So this is a fun little thing that you can play around with. But notice, still, the rows, the amount of columns of the first matrix has to equal the amount of rows of the second matrix. As I press this plus button, you see how as my columns expand, my rows have to expand for those two things to be compatible with each other. So that's pretty cool. Now let's get back to this. All right, so this is the matrix I want to focus on. Now let's say that I multiply this matrix right over here. Let's say I multiply it with the vector 0, 1. And once again, notice that this vector right over here is just I hat, right? That's the unit vector in the x direction. And notice how this vector right over here is just j hat. That's the unit vector in the y direction. So keep note of that. All right, so when I do my matrix multiplication, well, once again, now that you know a little bit more about this, try it out yourself. And note that if I have a 2 by 2 matrix, multiplying that by a 2 by 1 matrix, the resulting shape that I get is a 2 by 1 matrix. So let's see. 2 times 0 is going to be 0. And then 0 times 1 is going to be 0. 0 times 0 is 0. And 2 times 1 is going to be 2. So our resulting vector is going to be 0, 2. Okay. Now, what does it look like happening? What is this? What is this? Like, why is this even important in the first place? And I want you to look at the vector that we multiplied with, which is I hat. And notice how the result that I get is 2 times I hat. notice how when I'm multiplying by j hat, the vector that I get out is 2 times j hat. Whoa. So it looks like what this matrix does is, imagine if we have the vectors I hat, j hat on a coordinate plane. And what this matrix does is it transforms this coordinate plane so that each vector is 2 times longer. So any vector that I put into here, let's say if I have a vector from the origin to this point, whatever it is, if I multiply it by this matrix, it's going to expand. So it's going to get 2 times longer. All right. If it works for the unit vectors, it defines the transformation for the entire plane. And that is something that's extremely powerful. So I'm going to share this tab, and I'm just going to let you watch what's going to happen. So, okay, so let me see if I'm able to do this. Okay, so imagine if I have a matrix like this, very similar to the one we have. I'm just going to try to get, this is close enough, okay? But notice how this is 2, 0, and 0, 2. And so if I visualize this matrix multiplication to the entire plane, notice what happens. The vectors just get 2 times longer, and so did everything else, right? Everything else just gets 2 times longer, right? Now, I want you to focus on, let's say, this point right over here. Focus on any single point. It just gets 2 times longer, right? This point moved from here all the way up to here. And so that's something that's really, really cool. In fact, this matrix, this specific matrix that we have is kind of like, it's a scaling matrix, okay? So you can kind of think about this first number right over here as the scale factor in the x direction, right? Because when we're doing this matrix multiplication, right, notice how 2 times 1 gives me this 2 up here. So this is the scale factor in the x direction. And this number right over here is the scale factor in the y direction. Scaling matrices, so you see something like the scale factor in the x direction, 0, and then 0, scale factor in the y direction. Note that when it undergoes this transformation, the angles are preserved, right? If you have an angle of 90 degrees to the x-axis, it just gets 2 times longer. That angle is still 90 degrees. All right, so it kind of preserves, like, I guess, the overall shape, but it just makes everything bigger, or it can make everything smaller, or it can even do some, or it can even, as you might, predict, if I move this to -1 and I move this to -1 as well, it's just going to flip everything. So the coordinate plane just flips in the other direction. But notice how the entire transformation, once again, is just determined by what happens to the unit vectors. And that is the most important part. Now I'm going to be moving on to another concept in linear algebra. And surprisingly, it deals with area. You might be asking, what the hell am I talking about? How is area connected to linear algebra? Specifically, it's the area of a parallelogram. Imagine if I have vector A and vector B. Now, notice how this spans out to form a parallelogram. Parallelograms are useful for visualizing vectors. Notice how if I add vector A by vector B, it's the same thing as if I added vector B by vector A, right? The resulting vector that I create points to the same point. And so this kind of proves that if I add vector A by vector B, it's the same thing as if I added vector B by vector A, an important property, right? It's just like 1 plus 2, that gives me, or that's going to be equal to 2 plus 1, right? Let's say if I wanted to find out the area of the parallelogram that it creates. How am I going to do this? Well, area of a parallelogram is just going to be the base, which is just vector A. And specifically, it's going to be the magnitude of vector A because we only care about the lengths, right? So we're going to turn the vector quantity into a scalar quantity. So it's going to be the base, which is the magnitude of A, times the height, which is right over here. But we don't know the height yet. How do we get the height? Well, notice how there's an angle that's formed here. So if I take sine of this angle, what am I going to get? If I take sine of theta, I'm going to get opposite, which gives me my height, divided by the hypotenuse, which is just going to be the magnitude of vector B. And so the height is going to be sine of theta times the magnitude of vector B. It's going to be, I'm just going to write it like this, the magnitude of vector B times sine of theta. Okay. I'm going to be honest with you guys. I don't like this sine term. In like the dot product formula, we saw how there's cosines involved, and I really want to deal with cosine instead of sine. That's just not how I really like this. So I can say that the area of the parallelogram is equal to this, but I somehow want to find a way to write cosine into this. I know sine of an angle, that's going to be equal to cosine of pi over 2, or 90 degrees, minus that angle. All right, if you remember the complementary trig function rule thing you might remember back. Right, that's a property. If I rotate my vector by 90 degrees, now the magnitude of vector A prime is still going to be the same as the magnitude of vector A, because we know that when we rotate something, that doesn't change the length of it. So the magnitude of it still stays the same. And what about the angle right over here? Instead of this angle right over here, if I have vector B down here, notice how it forms an angle in between here, which I'm going to call theta prime. Okay. Now theta prime, what is that equal to? Theta prime is just going to be 90 degrees minus my initial angle, right? Because if I have 90 degrees here and I subtract it by this angle, well, then I'm just going to be left with this angle here. So it's going to be 90 degrees, which is the same thing as pi over 2 minus my original angle. Oh, I know that sine of the angle. And you see now we're able to apply this rule, right? We know that sine of the original angle is going to be equal to cosine of this new angle that we have, right? And so instead of sine of this angle, so sine of my original angle is going to be equal to cosine of this new angle that I create if I rotate vector A by 90 degrees, okay? Now notice how this looks kind of like a dot product. And that's true. This is just going to be the dot product between my vector A prime and vector B, right? It gives me magnitude of vector A prime times magnitude of B times cosine of A prime. Now, this is another niche thing that you have to recall back from maybe high school or middle school. When you have a point, and let's say the coordinates of this point is x comma y, when you rotate this point by 90 degrees, so if I rotate this point by 90 degrees, the new coordinates of this point is going to be negative y comma x. All right. So that's just one of the properties of rotating by 90 degrees. And if I rotate by another 90 degrees, aka by 180 degrees, I get negative x comma negative y. So let's say that initially vector A, that had the components of AB. And let's say that vector B initially had the components of CD. If I have vector A prime, and that's vector A rotated by 90 degrees, well then what I'm going to do is I'm just going to swap the components. So instead of AB, vector A prime would just be equal to BA, and I would just negate the B, right? So you just swap the components and you negate the Y1 that was originally there. And so if I take the dot product between negative BA and CD, or yeah, negative BA by CD, I'm just going to get A times D minus B times C, okay? And that's going to give me the area of this parallelogram I have here, right? Because the dot product has to be equal to this right over here, which we know is also the area of the parallelogram. So this actually has a special value, and this is something called the determinant of the matrix. And so the determinant of the matrix can be found. So imagine if I have vector A, which is AB, and I have vector B, which is CD. In order to find the area of the parallelogram, I just have to multiply AD minus BC. So diagonal to diagonal, okay? And that's all there is to it. So if you're given a problem where it's like, let's say if you have a matrix M, that's equal to 2, 3, 6, 4, and you want to find the area of the parallelogram, well, you just have to, the area of the parallelogram formed by these two vectors, or you can view the first part of the matrix as a vector, second part of the matrix as a vector. Well, the determinant of this matrix M is just going to be 2 times 4, which is 8, minus 3 times 6, which is 18, which is negative 10. Or if I have matrix M, which is equal to, 3, 5, and 6, 2, well, then the determinant of this matrix, 3 times 5 is 15, minus 6 times 2 is 12, gives me a parallelogram that has an area of 3. All right? Now, the determinant is very powerful. It tells you the area of the parallelogram, once again, tells you the area of the parallelogram that's formed through a matrix multiplication. So if I have 1 here, and I'm just going back to the matrix simulator, you see how these blue lines indicate like a sort of square, right? And then as a matrix transforms into new vectors based on the unit vectors, it forms a parallelogram, and the area of that parallelogram is given by the determinant. So if I show determinant, this would be the area of the parallelogram right here. Okay? if you originally have your unit vectors as the matrix, so imagine if I had the components 1, 0, 0, 1, notice how if I take the determinant of this matrix, well, 1 times 1 is 1, minus 0 is just going to be an area of 1. And the determinant, in addition, it can also be written as just a line, kind of like absolute value lines. So that's another way you might see it. But the determinant of the two unit vectors is going to be equal to 1. And that makes sense from this diagram. Notice how if I have a unit vector here and a unit vector here, this is just going to form a square. And the area of the square, well, this length is 1 because it's a unit vector. This length is also 1 because it's a unit vector. And so you just get the area of a square, which is 1. Let me just give you more intuition. So you see how this transformation right over here, right? I'm going to try and place it perfectly to 2, 0, but it seems like I can't do that. But notice how when this undergoes a transformation, it goes into an area of 4, right? We saw the scaling matrix that we saw before, right? If I double the length of the vectors, this just becomes a 2 by 2 square. And so I just get a determinant, aka area of this parallelogram, which is in this case a square of, well, 4. All squares are parallelograms, so that makes sense. Take a look at all you have learned in this video. And so just to kind of tie things up one last time, like a matrix defines a transformation of your unit vectors. And in turn, that defines like the transformation for like the entire plane. And so when you shift these unit vectors to a new space, right, that's going to have some area, most of the cases. So if you have your unit vectors I hat, j hat, and the transformation of the matrix shifts them to, let's say this becomes I hat and this becomes j hat, right? Notice how it forms a parallelogram. And so because the matrix shifts your unit vectors, well, then the resulting parallelogram that you can have, it can be a greater area than before or a smaller area than before, or even a negative area, depending on like if it flips around like some sort of axis, right? But we're going to get into that later, but just know that you transform, it creates parallelogram, determinant finds area of parallelogram. Now the determinant actually has a couple more uses, actually many more uses that we'll see later on. For example, let's say that if the determinant of the matrix is 0, and I want to visualize what happens when the determinant is 0. So let's say that I have a vector here, and so I want to multiply this to be equal to 4. So I'll move this up to 4. And you notice how when I eventually transform everything, these two vectors fall on the same line, meaning that this entire coordinate plane gets squished essentially into one single line. And that reduces a lot of information. Like think about it. We go from an entire coordinate plane, 2D, into a one-dimensional kind of line. And so when the determinant of a matrix is equal to 0, what that tells us is that, well, the area of the parallelogram that we have, well, that's just going to be 0, right? It's not going to have any area at all. Another interpretation when the determinant is equal to 0 is that you're going to be losing information. You're going from 2 dimensions to 1 dimension. And as a result, there's no way to undo this transformation, right? You can't undo this from 1 dimension to 2 dimension. You simply do not have enough information if you want to go back from this. And so this connects to something called an inverse of a matrix, where you have a transformation initially, and if you want to get back to your original state, well, you have the inverse matrix. And so when the determinant is 0, there is no inverse. You cannot undo this. And there's a final interpretation which deals with system of linear equations, which is something that's going to be talked about in future video. But this is all that I want you guys to take away, okay?